succeed or fail depending on whether you're a good juggler or not, but it will not depend on whether you're moving with uniform velocity. So the laws of juggling are the same in every inertial reference frame. The laws of mechanics are the same in every inertial reference frame. The laws, Newtonian laws of gravity, are the same in every inertial frame, according to Newton. What about the laws of electrical phenomena? Well, there was a clash. The clash had to do with Maxwell's equations. Maxwell's equations were the field equations, the field theory that governed the electromagnetic field and the way that it propagated and sent waves, electromagnetic waves, that we ordinarily call light or radio waves or so forth. And the fundamental dilemma, as you all know, I'm sure you all know, the fundamental dilemma was both according to, well, here was the dilemma. Maxwell's equations said light moves with a certain velocity. If you take the various constants that appear in Maxwell's equations and put them together in the right way, you get the velocity of waves moving down an axis. And that velocity comes out to be a certain number out of Maxwell's equations. You have two choices. One is to believe that Maxwell's equations are true laws of nature, as good as any other laws of nature, in which case the principle of relativity says they should be the same in every reference frame. But if it follows from Maxwell's equations that the speed of light is 3 times 10 to the 8th meters per second, which is about what it is, if it follows from Maxwell's equations that light moves that fast, and if Maxwell's equations are laws of physics, fundamental laws of physics, and if the laws of physics are the same in every reference frame, then the speed of light must be the same in every reference frame. But that was very hard to swallow, because if a light beam is going down that axis, and you chase it and run along with it at, let's say, 3/4 of the speed of light, then you ought to see that light ray moving much more slowly than 3 times 10 to the 8th meters per second relative to you. On the other hand, a light ray going in the other direction, since you're sort of running into it, you should see going even faster. So all these possibilities could not simultaneously be correct. That the laws of nature are the same in every reference frame, and that Maxwell's equations are laws of physics in the same sense that Newton's laws of physics, namely the same in every reference frame. Something had to give. Well, the point was, of course, that they were good laws of nature and that they were the same in every reference frame. The thing that had to give is our concepts of velocity, space, and time, and how we measure velocity, especially velocities which are up near the speed of light. Now, I'm not going to spend the full amount of time that I did previously on the special theory of relativity. That can be found on lectures from how long ago? They're on the internet, I believe. Relativity and electromagnetism. I think that was maybe about 3/4 ago. I've lost track. Yeah, they're up there. They're on the net. And they're the lectures on relativity, special relativity, and electromagnetic theory. We're just going to cut through it real fast. We're going to cut through the basic ideas of relativity a little more mathematically than I would do if I were teaching it for the first time. If I teach it the first time, I tend to teach it the way Einstein first conceived of it. How do you measure distances? How do you measure velocities? How does the propagation of light influence these things? Instead, I'm going to take a more mathematical view of it and think about the properties of various kinds of coordinate transformations. Coordinates now consist not only of x, y, and z, but also time, t. So imagine every event in the world is characterized by, just like every particle would be characterized by a position, x, y, and z, every event taking place in space-time is characterized by 4 coordinates, x, y, z, and t. Let's suppress for the moment y and z. let's just forget them for the moment and concentrate on x and t. That would be appropriate if we were mainly interested in motion along one axis. Let's focus on that. Motion along the x-axis. Let's suppose there is no motion along y and z. Then we can forget y and z for the moment, momentarily. We'll come back to them. And think of motion along x and t and the various reference frames that might be moving along the x-axis. All right, here's time vertically. Here's space horizontally. Physicists always draw space horizontally and time vertically. I found out that mathematicians, or at least certain computer scientists, always draw time